Hi guys, so today we're going to be learning how to solve a Brayton cycle problem using test apps. So let's go ahead and get started. So the problem states air enters the compressor of an ideal Brayton cycle at 125 kPa and 325 Kelvin with a volumetric flow rate of 4. The compressor ratio is 11. The turbine inlet temperature is 1025 Kelvin. So part 1 wants us to determine the thermal efficiency and the net power output. So let's go ahead and go to test apps. I'm going to go ahead and pull it up. So we're going to be using the gas power cycle test app, the PG model. So let's go ahead and start plugging things in. At state 1, it is 125 kPa, and we know that the temperature is 325. We also know volumetric flow rate of 4, and we can go ahead and calculate that. Let's go to state 2. We know that they gave us a compressive ratio, and so we can go ahead and calculate that. We know it's isentropic, so we can say S2 is equal to S1, and we know m dot is constant. Let's go ahead and calculate state 3. State 3, P is equal to 2. We know that we don't know anything about S, but we do know that m dot is constant, and we also know that state 3 has a temperature of 1025. Now let's go ahead and go to state 4, and that's actually equal, the pressure is equal to P1, and we know it's isentropic, and we also know that m dot is constant. Go ahead and calculate that, and let's go ahead and get the graphics panel, and we'll see that the TS diagram shows us all 4 states, and that's how we want them. Let's go to the device panel and let's start calculating the work and the heat. So with device 1, we're at a compressor, so we know the compressor is doing work, and so heat is 0. Go ahead and go to second device. It's from state 2 to state 3. We're dealing with a heat exchanger, and we know work is 0. We calculate that, and we go ahead and see state device 3. That's from state 3 to state 4. That's actually the turbine, and we know that that's doing work, so heat is 0. And so that's the work of the turbine. And then we go ahead and do our last heat exchanger, which is from state 4 to state 1. And we know work is 0. We'll go ahead and calculate that. And we see that is our heat out. We go to our cycle panel, and we're basically done with part 1. This tells us the network output, which is approximately 1013 kilowatts, and here tells us the thermal efficiency, and that is 49.6%. So we had solved part 1. Now let's go ahead and look at part 2. So part 2 says to assume the compressor efficiency is 85% and the turbine efficiency is 80%. So what this means is that we're actually dealing with an actual Brayton cycle, and so the TS diagram will look a little bit different. And let's go ahead and start solving for this. So I'm just going to go ahead and pull up a different thermal fluids panel. I have already put in state 1. It's the same as the previous state. For state 2, we're going to treat it as an ideal one because we'll need to calculate the ideal in order to calculate for the rest. So, or for state 3. And that's actually that. And we know m dot is constant. So this is the same as before, but now we're dealing with state 3. So state 3, we actually know that it's P is the pressure is from state 2, and we know that m dot is constant. What we know about T3 though, our new information, is our efficiency. So this is what I had done already. The efficiency of the compressor is actually 85%, and so we can actually calculate the temperature of state 3, the actual temperature, and using the efficiency. So this is what the temperature actually is. And so we go ahead and plug that in to test apps. So it actually equals T1 plus T2 minus T1 divided by 0.85. We calculate that, and now our state 4, now we have our state 3, and so now we can calculate our state 3, which actually is from our previous cycle, our state 3. So this is actually the turbine, and we know m dot is constant. And now we have our state 4, and we can calculate our state 5, and we'll treat it as the ideal part. So that's actually the heat exchanger, and we know it's isentropic. And we also know m dot is constant. And we go ahead and calculate this. And then we go ahead and deal with our state 6. So now we're actually dealing with the actual turbine state, and we can see that through this right here, and we can calculate temperature 6 using this equation here because they gave us the efficiency of the turbine. And so we know that it is equal to P1, and m dot is constant, and we have it equal to T4. It's going to equal to T4 minus 0.8 multiplied by T4 minus T5. And we go ahead and calculate that. Now we have our state 6, and now we go to our graphics panel, and this is the exact same TS diagram that I drew up. And now we go to our device panel, and we do the same as before, but with our actual states. So state 1 to state 2, that is dealing with the compressor, or I'm sorry, from state 3, that's dealing with the compressor, and heat 0, and that's our actual work of the compressor now. And we go ahead and do our second device. This is the same as before, but using our actual states. And that's 0. And now we're dealing with from state 4. What did we do? Yeah, so state 4 to state 6. Right, state 6. And that is our turbine. And so we know heat is 0. And we have our last device, which is our last heat exchanger, and that is from state 6 to state 1, and we know work is 0, and we calculate that, and we're all done again. And so we go to our cycle panel, and we see that the net work output is 162, and the thermal efficiency is about 9%. And so just to recap, we changed the efficiency of the compressor and the efficiency of the turbine, and this is in comparison. So we see that the thermal efficiency drastically decreased and that the net power output drastically decreased as well. So I hope this was helpful. Thank you for watching, and see you next time. Thank you.